Hi everyone, and welcome to our lecture on implementing convolutions. So in the last lecture, we described kind of the mathematics of convolutions, how we what the operation of convolution is, and how we implement this from a standpoint of automatic differentiation. But today we're going to talk about actually how we implement it in code. So how do you really code a convolution? And we'll actually go through a few different ways of coding convolutions. First, as sort of an explicit set of for loops, then as a set of sort of normal matrix multiplications with operations or with the tensors we already have, and finally as a sort of one big matrix operation using what's called the im-to-call operation. Right? And we'll show how to do that kind of efficiently using correct techniques from matrix striding. Now, it may seem, and if you sort of covered the lectures last time, it may seem like some of these operations are somewhat complex, right? Especially for 2D matrices and things like this, for 2D images. How do you really create the proper matrices? This might seem like a very sort of arduous task. But as we'll show today, it actually ends up being quite simple with the use of these very nice kind of striding tricks. Right? So let's jump right in and kind of get started with implementing convolutions. Now, I will actually start this off by live coding this. So I'm actually going to code everything here in the notebook. And this notebook that I'm going to be coding into will be, you can download it on the course webpage. But I would actually encourage everyone following along to just go ahead and implement with me as I'm doing these things, right? Even just copying code verbatim can be a very instructive process. And so I would really sort of recommend you all do that. Though, of course, the notebook with all the code implemented will be available on the course website. All right. So the first thing we're going to talk about in this lecture is storage order. So storage order deals with sort of how we store the tensors involved with multiplication of matrices, with convolutions in memory, right? And so you've learned a lot about storage of sort of traditional matrices, like with strides and row order and column, row major order and column order, row major order and column major order. But in the case of convolutions, we actually have larger tensors, and we need to know how to store these things and what's the right way of storing these in memory. So I'm going to switch over to my iPad here briefly and talk about kind of the sizes involved with these things. So remember, the operator we're doing in a convolution. So we want to take a height by width image, which is really, height by width by channel tensor. And also this actually channel in tensor. And we want to convolve it with this, say, 3x3 filter, or really more generally kind of a k by k convolutional filter. Right? But remember, in our notation here, each cell here was actually itself a C in by C out. I guess actually it was C out by C in was the convention we used. C out by C in matrix. And so doing this, we sort of want to kind of form these in the right way, such that they're sort of stored properly. And so in particular, we need to store input images, we will need a C in by height by width, so rank 3 tensor, but we're actually going to make a rank 4 tensor because we're going to include a batch dimension. And then for storing weights, we need a K by C out by C in tensor. But we'll talk about how to store these in a second. Okay, so let's go back to our code here. The most obvious way to store our input images is in this format here, right? So we're going to store them as a multidimensional tensor, a 4-dimensional tensor, where the first dimension indexes over batches. The second dimension indexes over the height of the image. So batches, if you have a batch size of 64, this would be 64 elements there. Then the height and the width of the image, and then channels. Okay, this is an ordering. This is sort of a standard way of ordering it. Channels is the number of the input image. Usually have 3 channels. It's a color image, but it can have other amounts of channels as well. Now this is something known as NHWC format. If you've seen sort of ordering of tensors before, you may have seen things like this before. And you may also know that there are alternatives, right? We could actually order things in other ways too. We could order them in, batches sort of first is kind of always a standard, and you kind of want to have height width next to each other. But actually, PyTorch as a library defaults to actually the NCHW format, which means that you first have batches in memory, then channels, then height, then width. All right, so PyTorch actually uses this NCWH format. And I kind of, I'm opinionated here, but I kind of want to say that that's the wrong format. As we'll see in a second, the way you implement these operations, because they are matrix multiplies, where sort of it's natural to have the channel dimension as the last dimension, I would argue that NHWC is the right order for storing images, and the one that PyTorch uses is the wrong order. It's very rare that I disagree with PyTorch's kind of choices in their design architecture, but here I really disagree with it. I really think that storing them in this way, as we're going to for Needle, makes a lot more sense, and just makes much more sense in terms of the operations that are actually done. In terms of the conversion to matrix multiplication, it's much easier this way. I know there are some advantages also for the way that PyTorch does it. Usually actually things like the batch storm operators are faster that way. But I mean, I'd rather specialize for the convolutional operators personally. So we're going to think of all our inputs as being 4-dimensional tensors stored as first the batches in the first dimension, then height, then width, indexing over the sort of the where you are in the image, then where you are in the where you are in the y direction, where you are in the x direction, and then where you are in the channels. Okay, so that's going to be our format for how we store images. The next sort of question is how we store our kernel weights. How do we store our filters? And here, again, we have 2 kernel size by kernel size dimensions, plus in channels plus out channels. And so the way we're going to do it here is actually exactly by storing it by first dimension is going to be, again, is the 4D tensor, with the first dimension being indexing over the kernel dimensions, second one indexing over the kernel size, then in channels, then output channels. Okay, so we're going to store these as 4 tensors in rank 4 tensors in this order. Again, this is not how PyTorch does things. Again, I think they are wrong for doing it the way they're doing it, but you know, they made these decisions. And they store it actually in the order of out channels by in channels by kernel size, but you know, that's just life. We have to deal with what PyTorch's decisions. Okay. And so let me just like talk for a second about what I mean by the ordering, going back to my picture here. So what I mean by the ordering is that, you know, we'd have our weights, for example, in this, and I'm actually gonna erase this because even though I talked before about them being C out by C in, I'm actually gonna write C in by C out now. That's how we'll do it today in this lecture. We wrote sort of mathematically in a different form last time, but let's not worry about that too much. What I mean is that we have some filter weights, right? We have some weights here, which are stored. The first index would be sort of, I'll call this, I don't know, I, right, which indexes sort of where we are in the filters. That would be, say, you know, if I is 1, then we are here. And then there's a j term, which indexes sort of, so this is I. Then we have the j term, which indexes how far we are kind of in that direction in our filter. And so this, I guess, would be I equals 1 and j equals 0 here. And then we have, remember, each one of these sort of boxes here, filters here, you should think of as a matrix. So of course, we're going to have an index. If we want to find a single value, we'd have an index into the matrix too. And so this would be, you know, the index of the, I guess I'd call it like, I don't want to use the word, well, I've already used the term K. There's too many indexes here, but let's just use like S and R to index over which location we're in. So this would be, you know, if you blow up one of these things, right? So if you take one of these things and kind of blow it up into a big matrix, this would be kind of where we are in the S row and the J and the Rth column or something like this. Oops, I went off the side there. The S row and the Rth column or something like that. Okay. So that's what I mean by indexing them. It means that these things are great big tensors, and you have to index the individual elements if you want a single scalar value. But really, it's much better to think, and except for the very first version we do, it's much better to think about these things as tensors. And we'll talk about how that actually makes things our life simpler in the big picture. Okay, so let's get back to the implementation now. We're going to implement our images in this format here, and are going to implement our weights in this format here. So that's going to be how we store basically the arrays, the multidimensional tensors, or multidimensional arrays, the actual storage, right, in memory of our input image and our output. All right, so now let's talk about the different ways we can go about implementing convolutions. And the first of these is kind of the obvious one. We can do it just as with a for loop, right? So we can implement a convolution as a for loop. I mean, we have to index over all the batches. It's quite deep, or I shouldn't say for loop, many for loops, right? We have to index over the batches, then over the channels, then over the, you know, each channel, you have to, go over each position and convolve it with each location in the filter. But you can do that. It ends up being like the deepest, I think it's like a 7-layer deep, or something like that. for loop, which is quite deep for the for loops I've ever implemented, but we can do it. Before we do that though, I'm gonna do something that all of you should do first before you design many of these things, which is I'm gonna write kind of a reference solution that we want to target. We want to be making sure that our implementations are correct, and so we're gonna use a reference solution to sort of verify that our implementations are in fact correct. Now, if you're implementing something from brand new from scratch, right? So you're implementing a library that's never, or some operation that's never been done before. There's a this is tricky, right? You have to sort of, you're writing it for the first time, you have to make your own reference implementation. But here we sort of have the benefit that convolutions already exist. There's lots of convolutions out there already. And so what we can do is we can actually leverage existing libraries to sort of give us a reference implementation of convolutions. And we're going to do this. And in fact, in this lecture, we're going to implement these things. We're going to use PyTorch as a reference implementation for our convolutions. Now, as I said before, the goal of this class in some sense is to write everything yourself, right? To not use PyTorch. But when you're writing test cases, initial test cases, it's really valuable. These things do exist, and you're free to use things like PyTorch as reference solutions to make sure that your code is doing the correct thing, okay? That obviously does not work in all cases, but at this point, I mean, even if you actually wanted to create a new deep learning framework right now, you could do that. So you could just use PyTorch as a reference solution. And so in fact, we're going to do this. All right, so the first thing we're going to do is we're going to implement a reference solution in PyTorch. So I'm going to import PyTorch, and I implement torch, the neural network components, and I'm going to define the convolution reference, which is going to take my input image Z and some filter weights, call weight. Okay, so the first thing we have to do in a reference implementation is convert this from PyTorch's, or from our, nice, good format, which is batch, height, width, channel, to PyTorch's, because we're going to do our convolutions in PyTorch, we have to convert from our nice NHWC to PyTorch's horrible NCWH format, okay? So let's do like NH, or N, yeah, so we're forming our tensors in this nice format, and we're going to convert to PyTorch's annoying format. So we're going to find this, ztorch is going to be torch.tensor. I'm going to create a copy of it so I don't, accidentally erase memory or so. We're going to do our implementations, I should mention, in NumPy. Of course, you could do it in the ND array, and you will do it for the homework. But, given that I'm not going to give away too much here in the lecture, I'm going to do it in NumPy, and we'll represent our inputs to this function here in NumPy. So we convert to a tensor, and then we're going to permute it to have the correct format. So that would be, the first dimension would be the batch, then the channels, then the height and the width. Okay. So that converts it to PyTorch's internal format now, because this channel 3 is the in our notation is the channels, and we want to put that first, and similar for all the rest. Okay, and I got to the same for the W's, so I have to convert W's to the in-channel, out-channel format. So I'm going to permute this to be okay. So I'll just write it here what I'm doing. So our input channel would be kernel size by kernel size by input channels by output channels, and PyTorch's is output input kernel. And so again, I need that would be, so I want first 3, and I think actually it flips the order of these things too. So I want actually 3, 2, 0, 1 for mine. Sorry, no, I need input, right? So I need input, output, and Torch uses output input, I believe. I don't know why. That seems like the wrong decision again, but they're doing it that way. Okay, so give us a little bit more space here, and then now we're going to call our convolution. So we're going to call out, and we'll use this like nn.functional call here. Hopefully I have that right. I haven't loaded it yet. conv2d, functional.conv2d, and I'm going to call ztorch and wtorch. And I'll return, I want to return a permuted version of it sort of back in our format. So I'm going to return out.permute, and I want to convert it back to this format here. So permute just swaps the axes. It's like the permute function or the swap axes function that you have in NumPy and the, I forget what we call it in the array, but I think it's either permute or swap axes. And this is going to undo that one. So this is going to be 0, 2, 3, 1. And then we want to convert to a NumPy array. And I'm even going to go to contiguous. That contains a contiguous array. You have to do that before you call NumPy sometimes, but I'm going to do it like that. Okay, and that should be our function there. Let's test it out. Let's create some matrices here in PyTorch or in sorry, NumPy. So let's, did I import NumPy yet? I didn't import NumPy. I should have to do it up here. Okay, and then let's say that z equals np.random.randan. Let's do a batch size 10, 32 by 32 images with 8 channels. Okay, and let's make our kernel, let's see, it's, let's say it's 3 by 3, mapping from 8 channels to 16 channels. Okay, and then outs is going to be, let's make it conv reference, zw, and let's just print what the shape is. Okay, so that's actually properly, I wonder why it's, yeah, so there's some NN pack there that couldn't be initialized. And this is actually proper. So notice we actually didn't implement any padding here. So we just have kind of a convolution without padding. It turns out for our actual implementation, what you will do if you want to add padding, just for simplicity, we could do it differently if we wanted, but we'll actually explicitly form the padding. It's given that as we see, we're going to be copying memory a fair amount anyway in these implementations. It doesn't matter too much to have padding, so we're going to do sort of padding-free convolutions here. And that means that the output size is, because we have a 3 by 3 kernel, we are convolving a 32 by 32 image, and so the output size is going to be 30 by 30, right? Because you lose 1 pixel off each side of the image. All right, so now, to compare, so this is sort of, you know, this is an implementation of convolution, but of course we're cheating. We didn't implement anything. We just called PyTorch after some permutations here. Let's implement our own version of this convolution. Okay, so let's do what I'll call like the naive convolution here, which is the simplest possible convolutional operator you could have, which just does this with a whole bunch of for loops. And as I said, I think this is like the biggest number of for loops I've ever had in a function before. All right, so the first thing we'll do is let's just get our sizes. So it's sort of helpful to have these things all as sizes. So I'll call this as z.shape should be, you know, our batch size, height, width, and input channel size is the shape of z. The kernel size, and let's just assume that the kernel size are the same. You could have different size kernels, but everyone uses the same size kernel anyway, so that's all you have to implement. And so the kernel size, cin we already know, and so cout is equal to weight.shape. And now let's go through the actual implementation of convolution. So the first thing we're going to do is we're going to initialize our output, and that's going to be a bunch of zeros, which are of size. Well, we have to specify the size, what this is going to be. Well, it's going to be number of batches is the first dimension of the size, and then the height of the new kernel is going to be h, but it's not h itself, right? Because we're shrinking the kernel, so we're shrinking the size of the image, and so every point we shrink it by on each side we shrink it by sort of like, you know, k over 2 or k minus 1 over 2, and so the end effect is that the actual size of the output will be h minus the kernel size plus 1. So the kernel size is 3, that means to subtract 2 off of everything. If the kernel size is 5, that means to subtract 4 off of everything, etc. Right? And so this is the resulting size of our kernel. And let's do cout because it's the number of channels out. Okay, now let's do sort of the largest for loop you've ever seen in a real function. And we're also doing it in Python, so this is going to be, as you might imagine, like the slowest possible implementation you can ever really imagine of these things. But let's go ahead and do it. Okay, so what does a convolution do? Well, first of all, let's just iterate over the examples in our mini batch, and then let's iterate over the output. So the input and the output channels. All right, so let's iterate over for cin in the range cin, then for cout in range cout. Now what we're going to do, now we have a sort of single input channel, a single output channel. Now we have to actually run a convolution, right? So what does a convolution do? Well, it moves sort of the center position over the entire span of the image, right? So we have to sort of iterate over x and y in the range of allowable outputs. All right, so let's first iterate over y, and that would y from 0 to the height of the output image, and let's iterate over x in the range of minus k to 1, the range of the output image. Okay? So now we're implementing over like the output position, and then we implement over the position in the kernel matrix itself, right? So that's the next thing we index over, is like where the kernel is as well. And this is now a bit sort of tricky exactly where it goes here, but if you sort of look at all your indices correctly here, what you would do is you would implement over from I in range k, so that implements over like where in the filter we're convolving the image, and then j in range k, and now you set the output image. So you set the output at this location, this mini batch, this x, this y, channel C out, plus equals, well, the image at that location, but not that location actually, that location plus the sort of the input that we want, right? The actual input in our image. And so the input in our image that we want to get was this be the same thing, but it's shifted over by I and by j, right? So x plus j, x plus, and then C in. And then times the weights, well, that would be, the weights would be the ij location in the weights, because that's sort of the kernel position, and then position C in and C out. I'm going to run into myself here. Okay, I think that is everything. I think that's our function. That's our big for loop. If I didn't make any mistakes there. Let's test it. I think I actually have the code to test this down. So let's make out2 here equal to the naive convolution of z and w. And let's print out the difference between out minus out2. Oops, what did I do? What I said, weight. Okay. And not surprisingly, this takes some time because that's a whole lot of for loops for Python to handle. Let's see, it's 1, 2, 3. Oh, I forgot to return. That's also a problem. All right. So it's how many for loops? It's 1, 2, 3, 4, 5, 6, 7. 7 layers deep for loop. But we are in fact implementing the convolution correctly, and we have the correct convolution. So I mean, what I'm doing is I'm printing the difference. Out was our was the output we got from the reference solution, and out2 was this was the answer we got from our sort of naive for loop implementation, and that is that they are the same, right? So there's no difference between the two. Implementing convolutions correctly. You can look at out2.shape and stuff like that. It's going to be, of course, the same size as what we want as out shape. Otherwise, the call before would not work. But this is not a very good way of doing things, right? So, I mean, you can just sort of look at the time of these things. So, what's the time it takes to run conv naive between z and w? Let's just look at that, and while that's running, I'll write the code to time, and I'll actually use timeit. Timeit runs a few different iterations there. So it took 7 seconds to do. Let's run with PyTorch's calls. It'll actually be dominated the time by like the overhead and calling them, so it'll actually vary a lot when you call it each time. So let's actually call timeit. Let's call the reference implementation of these two. It's going to run it a bunch of times now, so it's actually running it like hundreds of times. But on average, it takes like very, very little time to run this, right? Less than a microsecond to run these things. And so this is not, I mean, this is not what you want it to do, right? So we're doing a very, very long call. And this is not even that large of an image here, right? It's only a batch of 100, 32 by 32 by 8. Took us 7 seconds to do one convolution, whereas PyTorch, not surprisingly, still on CPU, but not surprisingly, takes less than a millisecond to run that. So not exactly, not exactly fast enough for our implementation there. Of course, it's no surprise, doing these things as a 7-layer deep for loop in Python is not maybe the best idea to do. Okay, so let's move on now and do a much better version of convolution, which is actually going to be almost as good as our final version, but which is going to which is going to be in some sense like I would say sort of like still the wrong way of doing it, right? So it's still going to involve for loops in Python and sort of too many calls in your automatic differentiation tool if you did it all in the automatic differentiation library. So it's a reasonable way of doing convolutions actually, but especially as your filter sizes get too big, this winds up being not that efficient. All right, so let me talk now about convolutions as matrix multiplication. So if you remember from before, we had this notion that a convolution kind of was a matrix multiplication, right? So you could think of the filters themselves, the filter positions, as let me go back to my iPad here for a second. Is that working? Let's go. Okay. We had these filter positions that were, each kind of a mess of a figure now. Let me erase this here. The filter positions in our image, in our convolutional filter, they were all themselves matrices, right? And we multiply, and the way to think about these things is we're multiplying this matrix by the vectors in our image, okay? So our images are vectors, and we're taking each of those vectors, we're multiplying it by that matrix, right? That was the way of thinking about where each cell here, each component in our filter was a matrix. All right, so what this means, though, is that if we were to think about the simplest possible case, where our filter was a 1-by-1 filter, right? So suppose k was equal to 1. In this case, doing a convolution, a 1-by-1 convolution, is just a matrix multiply. Okay, so that's actually very simple. It's just a matrix multiplication. That's all a convolution is. All right, and so let's go back and let's show how to implement a convolution as a matrix multiplication for a 1D convolution. Okay, so let's take our weights 1. Let's make sort of weights 1. I guess call it like W1 because our old was W. So let's make another W. Let's do this np.random.randan, a 1-by-1 convolutional filter, but still with 8 input channels and 16 output channels. So this is, in other words, just a 8-by-16 matrix. We're just putting it in the 1-1 location of our random matrix so that we can, of our filter matrix, so that we can actually compute this. So now let's look at what conv reference. I mean, this is still, we can still input this into our thing, and maybe let's print out the shape it is. So it properly sort of produces a matrix. Note that there's no change in size here because with a 1-by-1 filter, you don't miss any other elements here. Right? You still keep all the elements. So what this means, though, is that in this setting, we can implement convolutions with big quotes here very simply, right? It's just going to be equal to z times matrix multiply w. This won't quite work because that's not a matrix, so you have to actually look at the ww, the 1-1 entry there. So I should say out 2, the 1-1 entry there, and let's then look at the difference between the out and out 2. Minus out 2. Okay. Again, it's 0. So, we are properly implementing a convolution. Okay. And, as you sort of imagine, W, these are all the correct sizes, right? So W1, 0, 0, that's just going to be, I should look at the shape. That's just going to be an 8-by-16 matrix, and multiplying it by this is just a matrix product. Now, this is actually exploiting a property that's very convenient in NumPy, which is that when you multiply a matrix here, a tensor here, so remember Z is a rank 4 tensor, by a matrix, it treats all the leading dimensions just sort of as if they were sort of more and more rows in this matrix. Okay, so Z's a rank 4 tensor, but what it does is it basically treats Z as a matrix that is, all the first 3 dimensions by the last dimension, does that as a matrix multiply, and then reshapes it accordingly, okay? But we could do it explicitly here too, right? So this could all be done explicitly as well. So we could make this out, we could sort of write, if this is sort of too much cheating for you, because we're sort of, this is not a matrix, and we're doing matrix multiplies. If you want to do sort of real matrix multiplies, what you can do is you can do something like this. You could do like z.reshape, and something like the nice call here would be something like -1 and 8. That's just a nice feature that I have in NumPy that lets you sort of take all the leading dimensions of, well, let me just do this. So look at Z's shape first. Z is a 10 by 32 by 32 by 32, 10 by 32 by 32 by 8 tensor. And this now, if you do this, this would be a sort of 10 times 32 times 32 by 8 dimensional matrix. Okay, so we can take this matrix and we can multiply this one. This is now a matrix, like a real matrix. Multiply it by W1, 0, 0. Okay, and then that's our answer. But then we need to reshape it back into the size of z. So we can reshape this basically as z1 dot shape, or z dot shape 0, z dot shape 1, z dot shape, I mean, whatever. Let me just actually, since I used the actual sizes there before, so let me just do this. So this would be 10 by 32 by 32 by 8. Sorry, by 16, because I get 16 channels in the output. And I can just set out to, or else make it out 3 equals that, right? And, you know, I can do the same thing here and look at the norm difference between out minus out 3, and that is going to be 0, 2. Okay, so that is 1-by-1 convolutions. Of course, 1-by-1 convolutions are not very interesting. But the very cool thing here is what you can do, what you can sort of leverage by doing this, is you can actually use this same formula or the same strategy to do normal convolutions, not with just one matrix multiplication here, but with k by k of them, right? Because what we can do is we can take basically each location in W, do a matrix multiply between that and the original image. The original image, I should mention, sort of like the proper subset of the original image. We'll sort of see that in a second. And then just add all those up. And that also becomes a valid convolution. So let's see how this works a little bit. Okay, so let's find another function, which is going to be convolution with matrix multiply. And let's again have z and weight. And let me just copy up here what I had before. Let's copy this, because this is all the same. Nothing here changes. We're still creating, you know, we still want the same sizes, and then we're going to create an output, which is the same size. But now we can actually do this in a we can do the whole sort of instead of, you know, 7 layers deep for loops, we can actually just do a 2-layer deep for loop. So what we're going to do is we're just going to implement, iterate over the locations in the kernel matrix, and then use a matrix multiply to do everything else. So for I in range k, and then for j in range k, we're going to add the output, going to be plus equal, the input matrix, so it's going to be like the whole z here, so it's going to be z, all the batches, all the elements in the batch. We'll deal with these next. Let's do those two next. But all the output channels also, times the weight at location ij, which again is a matrix, right? So we're multiplying kind of that portion of the image by the corresponding weight. But this portion here is actually quite important. We need to figure out sort of where to put this. And what we have to do here is to sort of shift the image, shift the location we're multiplying with properly, such that we're in fact kind of sliding our filter over the whole image. And so what this would be is that rather than sort of the whole image here, which wouldn't work, right? That would just be like adding up all these multiplications applied to the same locations in the image. We have to sort of shift where we're convolving things with. So this is actually going to be starting at position I in the height, down to, well, it's going to be I plus H minus K plus 1. And this one's similarly going to be to J plus W minus K plus 1. All right. And that's return it. And this is now our new matrix multiplication carried out with just 2 layers deep of a for loop, where we're doing kind of the hard work using a batch matrix multiply. Okay. So let's actually do the same thing as before. Let's make some, I'm going to make them a bit bigger because now we can actually, I couldn't have made it this big before. It would have taken too long to actually run. But I'm making a batch size 100 now just to have a bit more, just take it a bit longer to run all these things. Our filter is going to be 8 by 16, and we're going to say out equals conv reference of z and w, and out 2 is going to be conv matrix multiply between z and w. And then we're going to look at the difference between out and out w, out minus out w. Out 2. Oops, what did I do here? Just misspelled norm. Okay, and it's not quite 0, but that's 0 numerically, right? So it's essentially, those are, in fact, again, giving the same solution to numerical precision and doing it here with 2 loops, 2 for loops, instead of a whole lot more for loops. Okay, so that is actually already a totally reasonable way of doing matrix multiplication. And you, in fact, could just probably stop, or sorry, doing convolutions via matrix multiplication, with one little for loop here, or two little for loops. But I mean, these 3x3 filters, this is, a loop of size 9 in PyTorch. Maybe it's not that bad. Maybe it's probably fine. But for the sake of both understanding how these things work and honestly, as an illustration of the single coolest call that NumPy has, we're going to talk about how to do this kind of in the proper way. And we're going to do it with this im to call kind of routine. All right, so what do I mean by that? So you remember what last time I talked about this, this way of sort of writing matrix multiplies or writing convolutions in terms of matrix multiplies, right? And so I sort of said that, okay, we have a convolution. If we have like a element 5 matrix, I'm going to get this wrong here, x2, x3, x4, x5. I guess I had zeros before, so let me just erase those. But you can look back in the previous lecture for this. I'll put the zeros there. If I want to convolve it with like a three-dimensional filter just in 1D, right? I could do this by basically writing this as some matrix that contains kind of all the versions that we have of this matrix, of this sort of input matrix, shifted over by the proper amount. So it had, 0, x1, x2, then x1, x2, x3, x2, x3, x4, etc., all just multiplied by a big vector of this. And the important thing to note is that this all still works when these are replaced and no longer are no longer just images, or are no longer just sort of scalars, but are now matrices and vectors, right? So if I can somehow shape my matrix into something like this, I can actually perform the convolution and then maybe stack my weights. And it's a little bit more complex in 2 dimensions, of course, but it's not that much more complex. And we'll see in 1 second how this actually works. Then I can actually do sort of my whole convolution in one go, just as one big matrix multiplication. And this is called the im to call operation. So im to call, m is written badly, im to call. And we want to be able to implement this in code. Okay, and now it might seem like, okay, that's great. This all makes sense here, but I mean, writing this matrix, that's going to require just as much effort as that for loop before, right? I have to iterate over all my positions, everything like this, and copy these and create a new matrix of the same size. That seems like a pain. But it turns out there's just a beautiful, beautiful way to write this whole thing, this whole construction of this matrix in like 5 lines of Python code that's actually very fast because we're using NumPy the whole time. And this uses this amazing function called the as-strided function. So to introduce as-strided so I think it's probably my favorite NumPy function that I guess, can you have favorite NumPy functions? I think I have a favorite NumPy function. Okay, to introduce the as-strided call, I'm going to actually go start with something that is not related to convolutions at all, but which is actually related to what we saw a few lectures ago when it came to efficient matrix multiplication. So you remember, we typically stored these matrices for an m by n matrix, right? We stored this in what we called row major format, meaning that, there were first all, we stored the last dimension contiguously, then the dimension after that, and if you have more dimensions, you sort of go more and more and more. But really what was happening is that we were storing this as a contiguous array, and then using strides in order to say how much we increment our memory for each successive dimension. Okay, and that's basically how we stored these things in memory. And if you remember what TQ mentioned separately, he made this point that if we have sort of matrices stored not just like this, but like this in some tiled format, then you can actually do the matrix multiplication more efficiently, right? Because you can leverage essentially cache locality to do batch operations, and not just cache locality, but also these sort of vector operations, even on a GPU, and certainly not even on a CPU, and certainly on a GPU, to do this much more efficiently. Okay, so this is sort of this notion of tiling matrices to do the operations like multiplication more efficiently. But you might sort of rightly ask, like, how do we get a matrix in this kind of form? I mean, they're usually, if someone hands you a matrix, it'll be in this form. I guess we could like write our own routine to copy these things all over, but that seems like kind of a waste. And it turns out it is a waste. You don't have to actually do this. So there actually are ways to use this amazing call called the there's this called this call here. So it's the np.lib.stridetricks.asstrided. And if you can't tell from that name, NumPy does not want you using this function. It's my best guess of why it's named like several layers deep in the NumPy internals here. But it's like, once you know how these things are stored, it's the most beautiful function, and you can implement all these things kind of just so quickly and so efficiently with them. So we're going to start by talking about how we can implement, not convolutions, we'll get that in a second, but how we can implement a routine that converts our data from this format to this format using the asstrided call. Okay. So actually, we're going to use two calls. We're going to use the asstrided call, but then we're also going to use the contiguous array call. So I'm going to introduce this kind of bit by bit here, but we'll sort of go through it in some detail. So at a high level, what asstrided does, what the asstrided call does, is it lets you take the memory of an array and refer to it as kind of the same array, but with different strides. You can kind of keep the same memory as it was before, but make it represent an array that consists of different like different strides in some sense. So you take the same memory, convert to a new array, but that new array has different strides. And so because of this, it actually represents a different tensor, a different multidimensional array, essentially. Okay. Okay, so that's a little bit opaque what I'm saying there. Let me actually give an example of what I mean by this. So let's generate a matrix here. Where's my cursor? Where am I? There I am. Okay, so let's start out by just implementing. Let's say like n equals 6 here, and make a equals np.arange. This is just gonna be a range from 0 to 6. I'm also going to make the float32 type, just I guess np.float32. And I'm going to reshape it to be an n by n matrix, okay? And then let's just look at what A is. Okay, so A is just a range. Okay, so A is just a 2D array that has kind of the numbers 0 through 35 in it here. Okay, so that is... that's that. Let's now start talking about how we go and actually look at how this memory is stored internally, how this data is stored internally in memory. Okay. Now, this data here, because we constructed it as sort of because it's in row major format, but also because we constructed it as just as an array and then reshaped it. This data here is going to be laid out contiguously in memory. So the memory itself will contain the numbers 0 through 35. And it actually is not that trivial to get the internal memory that NumPy, the internal memory storage that NumPy uses. NumPy, again, same with asstrided, NumPy at every step tries to prevent you from knowing how the data is stored internally. So there may be another way of doing this. I found this way a while ago, and I've always just used it. It was this call here. It is I use the C-types library, which is, again, how you interface with C code. So it naturally has the routines to do that. But what this does, we can print this call. I'm gonna create like a new buffer from the data, and I'm gonna call ctypes.string at a.ctypes.data, and then a.n bytes. Okay, and so this creates like a C string that corresponds to the actual underlying data of the NumPy array. If you just look at this data, for example, it'll actually rearrange it as we'll see in a second. And then you have to also change, I think, the data type. So I think you need to say in the buffer call itself, you need to say that this buffer, I want the d type to be equal to a dot d type, and the count, which is sort of how many types, how many locations it should read, would be a dot size. That's the number. That's the size of a. Did I do this wrong? I did something wrong here. D type, a dot d type. Oh, this is like that. There we go. Okay, so that sort of shows that this, I mean, this is not going to be so surprising right now. It will only be surprising when we see what happens differently. This is sort of how we access the data. So again, this is written out a bit more in the notebook, but this is sort of how things are stored internally. The other important element to look at is the strides property of the array. So this array, right, would have a stride. Remember, strides indicate the number of sort of locations in memory you move with each consecutive element, right? So here, we have a 2D array where moving one element in sort of the last dimension moves you over one location in memory, right? So go from here to here, you increment by, one unit, which in this case is 4 bytes, and to increment from here to here, you increment by 6 units, right? So the way you can find that out in NumPy is by looking at the strides operator. And NumPy has this weird convention that strides actually is stored in terms of the number of bytes, not in terms of the actual sort of number of elements, which is kind of non-standard. ND-array will use, I think PyTorch uses the number of elements. ND-array that you're implementing will also use the number of elements, not the number of bytes, but it's a pretty simple, because we used, float 32, and we're always going to use float 32 here, you just divide kind of by 4 to get kind of the normal strides for NumPy. Okay, so let's now do this big thing, and let's figure out how to convert this matrix here to one that is tiled in this form. Okay, so what I mean by that is we want to convert this matrix here, which is sort of a 6 by 6 matrix. We want to convert that to a matrix that looks like this, and we'll use a tile size of 2. So we want to convert it from a 6 by 6 matrix to a 3 by 3 by 2 by 2 tensor. Okay. Now, if we just did that, okay, so if we just did that, if we just took A and did this, then said reshape 3 by 3 by 2 by 2, this is actually not what we want, right? Because the first sort of tile here is sort of the first tile contiguously in memory, right? It would be 0, 1, 2, 3. But that's not actually the first tile here, right? The first tile is 0, 1, 6, 7. Second tile is 2, 3, 8, 9. Right, it would be like this term and this term. I can't highlight multiple lines here, but like the first tile would be these things here, right? So just reshape enough does not actually give us what we want. It doesn't really do what we want. So we have to do something else. So the question is, how can we? What we're going to do is we're going to use the as-strided call to create a new version of A that is the proper size and which is sort of has the proper strides in order to represent a proper tiling of that matrix here. Okay, so what do I mean by that? All right, here's where we're just going to get, actually, let me actually just even say, and since this is a pain to do every time, stride tricks as strided as, or rather from stride tricks import as strided. Okay, from, I guess, oh, it's NumPy. Okay, so we have our as strided call. Let's use our as strided call on A. And in particular here, you can kind of get help on this. So the arguments for as strided, the first argument is the first argument you can pass is the shape, then the strides. I don't ever worry about the sub OK and those sorts of things. And writable, I actually don't even know what those things do. But the important arguments here are the shape and the strides. Okay, so I think this is actually best shown by example. So I'm going to run as strided on the matrix A, where I'm going to pass as the shape we want, which is a 3 by 3 by 2 by 2 matrix, right? And now is the important part, which is we're going to pass the strides. And I'm going to pass the strides, I'm going to multiply, I'm going to pass this as an array. We can do it as a tuple too, but I'm just going to do it as an array so I can multiply it by 4, so I can do the strides in terms of the normal units. And the question is, for each of these dimensions, so now we're reshaping this as a rank 4 tensor. And the question I want to ask you is, what is the size that we need for the strides to get the tiling that we want? All right, so let me actually copy this. Maybe I'm gonna copy this down here, just so this is right above our call here. What strides do we want to make this the matrix we want? Okay, so we want to lay it out in memory like this. We want sort of these elements to be contiguous. Then these elements in sort of the first dimension should be this one. The next dimension should be that one. Then this one, etc. Right? And so as sort of a 3 by 3 by 2 by 2, 3 by 3 by 2 by 2 tensor, our first dimension would increase from this location to this location here, right? Does that make sense? I mean, we would basically, as we increment our first index, it should jump from this location to this location. All right, and what that means is our first stride value should be 12. Okay, so that's like the dimension of our first kind of skip dimension. How much we jump in the first dimension would be increment memory by 12. Okay, now let's talk about the next dimension. So the next dimension sort of indicates what cell we're in. So, this is like this here is like a 2 by 2 block, and we want to jump to this next 2 by 2 block here. That means the start of our in memory from our first from our first dimension to our second dimension goes from here to here. So our stride increment for the next dimension would be 2, because we jump over by 2 elements when we increment our next dimension. Okay, what about the third dimension? Well, the third dimension is sort of the dimension within our tile, like the height dimension within our tile. And so that would jump us from here to here in our third dimension. And so that would be a stride of equal to 6. And finally, the last stride value is our last dimension in our tile, and that just goes from there to there. So that's just going to be equal to 1. All right. So that's the whole call, actually. And we'll actually make this maybe equal to b. So b equals to this. All right, and then let's actually print b. Print b. Okay. And so the nice thing now is that b is also, first let me just print b.shape. So b is also a 3 by 3 by 2 by 2 matrix. But if you look at b, the elements of b, the first sort of element in B, or the first sort of grouping in B, is exactly this tile right here. Okay, I'm doing that, but it's this tile here and this tile there. So B is a 3 by 3 by 2 by 2 tensor where the indexes properly correspond to sort of the tiling that we want. Okay, but we're actually not done yet, because the as-strided call does not copy memory. So B points to, in fact, the exact same memory as A. I think you can even look at this. So if I change like B0 to be equal to, 5 or something, this should also change A0 to be 5 also. Oops, I've messed that up. B, unfortunately, I did destroy memory there. I set the whole index there to be that, but I meant to say B0000. I meant to do this, but let me recreate these things. So A is that, B is that. If I set the B last one, then A also as a matrix would have this thing here. So B points to the exact same memory as A. This is, by the way, why NumPy doesn't want you doing some of these things. Though that one happens even when you just copy memories normally, or matrices normally. So that one actually is pretty common. But it's very weird because you can now sort of manipulate it in different ways and like set different elements of it, right? So if I set like this element here to equal to 5, that will change this element down here, right? That will change this. Oops, this one, right? That will change this one here. Okay, so let's put this back the way it was and do that. So And of course, if we look at sort of this, our fancy function here, where was my function to, yeah. If we look at our fancy function here on looking at the sort of the memory of B, what we'll see is that like nothing's different. So B, in fact, if I replace B here with all of this, B is the exact same memory. So it's going to be still just the continuous elements in memory. Nothing changes. Okay. In order to actually change anything, we need to use what's called the as contiguous call. Okay. So what this does, and oh, and by the way, you can also look at b.strides here. So it can look at like the strides of B, and the strides of B, as you would imagine, correspond to the strides that we set in our as strided call, just multiplied by 4. Okay, so the problem here is that we haven't actually changed the layout in memory at all of our tensor, right? It's still stored in this order, so we can't do things like actually more efficient matrix multiplication and stuff like this, right? All we can do is just have a different view that NumPy knows about, but which is not very helpful for us. So if you want to actually change the matrix such that it's laid out in this order, so laid out in memory, like 0, 1, 6, 7, etc., we need to use the as contiguous array call. So we call C, for example, equals np.asContiguousSarray, calling B, and now we can print this whole thing here from C. Should probably have made this a function, but oh well. And what we see now is that this is now laid out in contiguous order according to this sort of 3 by 3 by 2 tiling of our array, right? So, you know, the memory as expected is 0, 1, 6, 7, then 2, 3, right? Then sort of like this block, this one, this one, this one, this one, then this one, this one, this one, this one, etc. And this is actually a really convenient way of generating a tiled matrix from a normal matrix, right? There's no for loop is required here. It's just this. I mean, I guess if you made it one thing, it would be np.asContiguousArray for this thing, but it's sort of one line of NumPy. You can create a tiled version of your array. Okay? And that's very convenient. Okay, so that actually is going to be sort of all for this. Oh, and actually, maybe before I do that, though, I should just mention that it's also possible to look at the strides of C, and the strides of C are contiguous in that the strides are sort of descending in order of the dimensions in the matrix, right? So they're not something weird like the strides of B, which we created ourselves using the as-strided call. They are contiguous. They're contiguous things. Okay, so that's actually all that we have now from the for the sort of this simple example of as contiguous array. Let's now talk about how we use this procedure to implement convolutions. Okay, so first of all, again, we're going to implement, remember, we're sort of, our convolutions themselves are going to be these sort of rank 4 tensors that make things kind of annoying. Let's actually, to keep things simple though, let's think about just doing a convolution with a sort of off a 2D image with a 1D with a 3 by 3 filter. Okay, so I'm going to go at scalar convolutions again. Though the nice thing here is that we'll be able to very easily extend this to the case of matrices and vectors, and we'll see this in a second. Okay, so here's our A matrix, and now let's suppose we want to convolve it with a filter that looks like this. That's just some like 3 by 3 filters. So let's make our 3 by 3 filter. Let's keep this all sort of as 2-dimensional things here. So let's make this A range 9 dot reshape. I guess I'll make the D type float 32 again, and reshape it to be 3 by 3. And so here's our filter that we're going to convolve this with. Okay. So recall that what we want to do with this operation here is we want to take this set of weights and kind of slide it over every 3 by 3 combination here. Okay, so I want to slide over this 3 by 3 combination, this 3 by 3 combination, this one, etc. All right, so now the big question is, can I create in this case, rank 4 tensor that would hold all the 3 by 3 locations here that I convolve this thing with, that I sort of overlap this thing with. Okay, so remember, there's going to be 4 positions that I'm going to create a 4 by 4 output image. So there's sort of 4 by 4 positions that I convolve this with, right? First, this one here, then this one here. Hopefully you can see my mouse okay on this. Then starting this one, then starting at that one. So that's 4 kind of in the X direction, and similarly 4 in the Y direction. All right, so can I somehow create a 4 by 4 by 3 by 3 matrix or tensor of all those different locations? Okay, so I'm gonna create some matrix B here, which is, actually I'm kind of giving away the answer there, but that's okay. How do I do that? Okay, so I'm gonna do this with the as-strided call, okay? So let's look at this again. All right, so we want our first block to be basically these 9 numbers here, right? Then we want our second block to be these 9 numbers, and our third block to be these 9 numbers, fourth block to be this one, and then our next dimension we jump by 1, okay? So how do we do that? Well, let's create an as-strided version of A. But of course, you know, that's just the first bit, right? Our shape, our output is going to be 4 by 4 by 3 by 3. That's the output size we want, and we want each block in this new block matrix, each 3 by 3 block, to be one of kind of these blocks of things we're going to be convolving with. Okay, so if I want my like 1 by 1 element to be this thing, when I move down in my first, so the first dimension kind of says, okay, I want this block here. If I move down in the first dimension, it should be this block here. Then that should be this block, you know, starting here. Then it should be this block starting here, etc. Okay. So how does that work? Well, what should be my first stride? Well, you know, if my first block starts there, my next block would start, you know, move this down by 1. My first stride number would be 6. All right, so strides equal np dot array again, so I can use actual normal strides, not NumPy strange strides. It'll be 6. Okay, so my first block that I have is this one. My next block though would be sort of this 3 by 3 block here. So it'd be this one, and this one, right? And therefore, you know, if I want to, if in my next dimension, incrementing that dimension by 1 moves me over by 1, well, the stride should just be 1, right? So the next stride is 1. Next, I want to know, okay, so within these 3 by 3 blocks now, how do I tile like that 3 by 3 block? Well, in the first dimension of that 3 by 3 block, if I increment, you know, from this position to this position, that moves 6 dimensions more in memory. So my next stride is going to be equal to 6. And then finally, if I'm with my last dimension, moving over this and 1, then that of course also is just a stride of 1. And so that is my stride of 1. Okay, and just to emphasize this takes, and by the way, if that all kind of went by fast, I would go through and read this some more. And sort of figure out what this is doing here. But what this does is this creates a new matrix. Let's maybe just look at b.shape first. So B is a 4 by 4 by 3 by 3 matrix where each block of B is exactly kind of one block that we are convolving with. Okay, so it's going to be one block that we're kind of going to convolve with. And then we're going to multiply it by this thing, right? So first we multiply this whole thing here by this one. Then we multiply it by this next one, right? So the first block here of this matrix here is kind of the upper left corner here. The next block of this matrix is the same position moved over by 1, etc. Okay, so that's sort of how we create this matrix, and actually that's the imp call. I mean, it takes a little bit more. It takes a little bit more kind of work to do this, but you know, I mean, for the like multi-dimensional case, but it's actually not that much work. It's essentially the same thing. Okay, so but how do we actually create a convolution of this, right? So like this is still just kind of this is just kind of, you know, creating the sort of the the shifted version of these things, right? It's not really creating a convolution. The way we create a convolution is we take this thing, though, and now we treat each of these elements as a vector, okay? And the cool thing about this is that we can actually just use, to do this, we can just use the reshape call. So we can call b.reshape. I guess that would be 4 by 4, so it's 16 by 9. And what that would be, oops, b.reshape. And what that is that's now the first element here. This first big kind of 3 by 3 block as a big vector, right? And then this 3 by 3 block as a big vector. So this is the first 3 by 3 block. This is the next 3 by 3 block. And so we can just multiply this thing by a similarly reshaped version of W. Let's reshape W to be 9-dimensional. That takes our filter here, multiplies it by each of these blocks, i.e. runs the convolution, and then finally we'll take the whole thing and we'll reshape it to be 4 by 4. And that is our convolution. Okay, so we've done our convolution essentially in one line of a call to sort of as strided plus reshape. Now, there's a very sort of important thing to note here, which is that some magic happened here. And actually a really sort of important bit of magic happened there. What happened here is that and actually also in the as contiguous array call, we took our memory and we compacted our memory. So we made these matrices contiguous in memory. And unlike the tiling case, where we did move stuff around the tiling case, but we kept the memory size the same. In doing this call here, we are actually expanding the size of the matrix, okay? So there is no way to have if we look at this, let me just make C equal to this just for the sake of it. If we look at, I'll go back and, so if we look at C, right? C has more elements than B does, right? Because we're repeating each location up to 3 times. And unlike the case of this tiling, there is no way to do that without copying memory, right? So this one term there occurs in more than one place. It occurs here and it occurs here. And actually one's a simple case because it appears towards a corner, so it's actually not that bad example. But 14, right? 14 occurs here, 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 lots of places, right? All over the place. Here, here, here. Okay, and there's no way around this. So this reshape call, and you can even see it. So if we sort of look at B before the reshape and look at B's strides, this is these funny strides that we specified. It's multiplied by 3, but it's 6, 1, 6, 1, essentially. But if we look at C.strides, C.strides is just a contiguous array. So C is a contiguous array. It's contiguous in memory. Everything is fine. If we do our kind of calls here to, let me find out my call to print C here, what we will find is that C is much larger, right? It actually has to store in contiguous memory all that data. So we are expanding our size of data when we do this. Okay, and that's really important to be aware of. So that's kind of actually all we need to do to call for multi-channel convolutions. Okay, and so the entirety of our convolution now is going to be done with one big to call just with a bit more care about manipulating our convolution. So I'm just going to write it here. I think it's actually easiest just to write out and see what this is. But I'm going to write a convolution which is to call with z and weight. And I'm going to look at I'm going to copy above here what my data was. Actually, before I do that, I didn't actually do this, but one thing I can also do here is just time these solutions. So I made a big deal of the timing of this before. Let's time this call. Oops, what happened here? Oh, I think I've created new matrices here. Gotta redo that. Okay. So I'm gonna time the call here. So it's 4.21 milliseconds. Let me do a similar version that calls sort of our This is our old tiled one. We'll do the same thing in a second with the int to call one, but I'm gonna time our old variant of this, and so it's about, it's quite a bit slower, and we can improve on this still. So we're going to improve on this bit with our int to call version. We're not going to get it to 4.2. They do additional optimizations, especially for really small kernel sizes like that. There's a lot of things you can do, but we are going to bring it down from this here. Okay, so let's sort of go and look at kind of our implementation here. Let's copy these because we're going to want some of these same things here. To call this, and we're also going to look at the strides. So let's look at like HS, WS, and CS as the z.strides. Okay. Now let's talk about like do a few additional things that kind of are useful here. We're going to look at the size that we want to have in our sort of matrix operation, right? We want to sort of make this whole thing a bunch of batch matrix multiplies. And I would go through kind of the description here if this doesn't make too much sense. Hopefully just the code makes sense. But what we're going to do is we're basically going to create a sort of a tiled version of our matrix of our input image where we're going to make each. So maybe go back to this one thing for a second. Going back to my Python or to my code for a second. Okay, I don't know why I can't switch. Here we go. Okay, so we're going to make a version of this thing where each of these is going to be a C-in by C-out matrix. And each of these is going to be sort of a properly sized variant of the whole vector, right? So it's going to be like a, so this whole matrix here in int to call would be a, so this dimension here would be basically, it would be k by c in. This would be c in by c out. And then this here would be, whatever dimension we need to sort of stack all the rows and columns together. Okay, that's the matrix we're going to create here. All right. So let's see how we do that. So we're going to create all these strides here. So the first thing I'm going to do is I'm going to talk about like what this inner dimension of like the size of the matrix we're going to multiply here. So I'll call like inner dim is going to be equal to k times c in. That's going to be like the inner dimension, like the number of columns in our final matrix. And I'm going to then make A as my as-strided call applied to Z, which is my image. The shape is going to be number of batches, shape equals number of batches times H minus K plus 1, then width minus K plus 1. And the output size is going to be that we want of K is this inner dimension, right? So this is, well, sorry, actually, it's going to be K by C in. We're going to then reshape it to be the right dimension. Okay, that's going to be the shape of my new matrix. I'm going to create a really kind of a temporary sixth order tensor. And then I'm going to set the strides equal to, well, the strides are going to be the number of just the normal stride of the batches. That one doesn't change. What I do with my things here is actually the exact same thing I did in the single dimensional case. It's going to be equal to the stride in H, the stride in width, and then you repeat the strides in H and width again. So that's sort of like, that was essentially this thing up here. We did the stride of, in this case, this was the height stride, this was the width stride, and this is the height stride, and this is the width stride. And so we're just doing that same thing again. And then we repeat the channel stride as well. Okay. And that's our strides. Right? Then we reshape this whole thing to be the second dimension. The number of columns is the inner dimension. So that sort of compresses these last three columns, flattens them out. The last two dimensions, it kind of flattens them out. And I'm going to set the first dimension to be -1. Then I just multiply my output rather is A times my weight.reshape Well, I want to flatten it in the kernel dimensions, and I want to just leave the cout dimension. And finally, I want to return a reshaped version of this, which is n h by h minus k plus 1, and w minus k plus 1, and cout. That's it. So that's the entirety of the imtcall, kind of reorganizing, kind of striding and overlapping, creating overlapping columns, all this kind of stuff. Let's test it, of course. Let's say out2 or out equals conv reference zw. Okay, I think it's the same size as there. Out2 equals conv imtcall z and w, and let's look at the norm difference between them. Out minus out2. Okay, and again, it's numerically the same thing. So I think this is like so cool, right? This is creating this like order 6 tensor that consists of overlapping blocks of the matrix, extracts all possible 3x3 blocks of the matrix, like with the proper channels and with the proper batch sizes, and then does the whole convolution in one single matrix multiplication. And what we do find is that this is quite a bit faster now. It's not going to touch the PyTorch version still. I think it's like, but I think it's going to be about twice as fast probably as doing the individual matrix multiplies. And that, of course, for things like, especially if you have smaller batch sizes, the difference here grows because the more you can do kind of in one big multiply, the better. So if I look at the time to get this one, the time here is, I think actually PyTorch has optimized their thing a lot, because last time I tried this on PyTorch, this was about 25% slower than the PyTorch implementation, but I think it's actually quite a bit slower now. So 14.4. So remember our one above here was our sort of naive, not super naive, but the next most naive one was 27. So we've basically sped it up by 2x. We've made it twice as fast. Still not to the 4.21 level, but quite a bit faster. Okay, so hopefully that kind of gives you a rough kind of idea of how we go about optimizing these things with imtcall. And the key idea here is that rather than sort of rearrange memory in some complicated fashion where you're explicitly doing copies and things like that, you can do a lot of that with this one nice sort of compact as strided call. And you can create very complex tilings and overlapping tilings, all sorts of stuff using just the as strided call of your NumPy. Now, one thing that is important, this is the final note of this sort of thing here, hiding it with my head here, is that the reshape call and the as contiguous array call, they hit a lot of logic. And actually, when you implement all of this in your own ND array library, as you will in, well, you won't implement the convolutions, that'll be homework 4, but you'll implement the calls like as strided in homework 3. When you implement the as contiguous array call, or we call it compact, to make it compact, contiguous in memory array, there's actually quite a bit of complexity there. So I'm writing this, look how fast this convolution is. It's just, a few lines of code. That's great. But the really 2 lines of actually meaningful code here, right? Just the as strided call and then the out call. I guess you could have even wrapped this reshaping with the thing. So but a lot is happening in actually the as strided call. Not much is happening at all. You're just literally taking the exact same memory and just creating a new matrix that has different strides. So this call itself is essentially free. There's nothing that happens here. Quite a bit happens in this call, though, in the reshape call, because the reshape call, that one compacts the array in memory, and a lot is happening there. And you will have to implement that compact call in homework 3, and it does take some time, especially for arbitrary size tensors, to get this right. You have to kind of use something like a stack or something like this. So be aware of that. There is quite a bit of hidden logic there, but again, the final thing, which I think is just beautiful here, is an entire 3x3 convolution of multiple channel, multiple batches, no padding here, just no padding. Padding you can add separately. This all is 2 lines of Python in NumPy. There aren't that complex lines, right? There's no like hidden convolution there. It's just using matrix manipulations and manipulating memory of matrices to call these things, which I think is just really cool. All right, so we'll see you next time when we talk about actually some more architectures in deep networks and some more things like that. But hopefully this gave you some idea of how powerful these sort of matrix manipulations really can be. Thanks, everyone, and see you next time.